Hello. Alright. Hello, guys. Alright, let's wait like a minute to get more people. Alright, so I also changed the timing of the class from, instead of last week we had 4 to 5, but we didn't quite get through the handout, so I changed it to 4 to 5:30 this time. Yes, it was fun. Alright, okay. Still got people coming. Alright, well, let's wait like 30 more seconds. Alright, okay, let's get started. So today, we're going to be looking at, Alright, so today we're going to be covering complex geometry. But first, before we look at complex geometry, let's go over just a couple properties of complex numbers that we need to understand complex geometry. So first, right, complex numbers are defined, right, z equals to a plus bi. So a complex number z is defined as a plus bi. Right, I'm sure you guys know this. B times I equals square root of -1, and then a and b are real numbers. Okay, so just a couple properties of complex numbers. So the conjugate of z is defined as a minus bi. And then the properties of the conjugate, we have, if we have two complex numbers w and z, then we have the conjugate is distributive across addition. So this equals to, and then the conjugate is also distributive across multiplication. So multiplication and division. So we have w over z conjugate equals to w conjugate over z conjugate, and then we also have w conjugate times z conjugate equals w times z. Alright, and then we also have, so we define, hold on, and then so we also have, right, the conjugate of z equals z. Alright, okay, so now we define the magnitude of z as z times z conjugate, or the magnitude of z squared. And so the magnitude of z squared is obviously just a squared plus b squared. And so the magnitude of z equals square root of a squared plus b squared. Alright? So if we graph the points on a coordinate plane with a corresponding to the y-axis and b corresponding to the x-axis, we end up with a complex plane. So if we have a coordinate z here, then this point corresponds to a plus bi. So where this is a, or sorry, where this is a, this is b, and this is a, and this is b, right? So we have a, and then that's the a-axis, that's the b-axis. So this point corresponds to a plus bi, and then you can see that the distance from the origin to the point z is equal to the magnitude of z, right? That's why it's called the magnitude of z. So one important property of complex numbers is that they are very helpful when they are written in polar coordinates. So this is just Cartesian coordinates, right? A plus bi. But, okay. Right, so, wow, more people. Okay, even more people. Okay. Alright, okay. anyway, so going back to where we're doing. So complex numbers can be, if we write these in polar coordinates, it's much easier to see. So polar coordinates, it's defined by the radius and the angle. So a complex number equals to r cosine theta plus r times I sine theta. And so the way we write this is r times cosine theta plus I sine theta. And so usually we abbreviate this as r cis theta, where cis just stands for cosine plus I sine of theta, right? And so an interesting theorem says that this cosine plus I sine theta is equal to r times e to the power of I theta. And so using this property, we find a number of interesting properties of z. Okay, so theta is called the argument, and r is the magnitude of z, because the magnitude of cis theta equals 1, right? And the magnitude of z equals the magnitude of r cis theta, which equals just r, because r is a real number. So the magnitude of z is equal to r, right? And then so we find some interesting properties. So the first one is what's called as de Moivre's theorem, where angles are additive in the complex theorem. So when we have a complex number z and a complex number w with argument theta 1 and theta 2, the product z times w has argument theta 1 plus theta 2. And this comes straight from the definition, right? Z is equal to r 1 times e to the power of I times theta 1, and w is equal to r2 times e to the power of I theta 2. And so the product of these two is going to be r1, r2 times e to the power of I times theta 1 plus theta 2. And so this shows that multiplication, it leads to both addition of the arguments and multiplication of the magnitudes. And so this, remember, derives from the earlier properties that we went over, the properties of the magnitude. So the magnitude of z equals to magnitude of z times magnitude of w, right? So anytime we want to rotate by angle of theta, we can simply so if I want to rotate in the complex plane, if I have a complex number z, so usually we draw this as a vector, if you guys know what that is, but for our purposes, we'll just draw it like this. And then so anytime I want to rotate this z, say alpha degrees to a different point, z prime, all we have to do is just multiply by cis theta. So if I want to rotate z by alpha degrees, we take z times cis alpha, or e to the power of I alpha, whichever one is more convenient. And so this shows us that dealing with rotations on the complex plane is far more easier than dealing with rotations on the normal Cartesian plane, because the equations for dealing with rotations on the Cartesian plane are much more complicated than the simple rotation, which is just z times cis theta. So anytime we want to deal with angles or rotations, we usually want to consider the complex plane, right? Okay, so a couple of other properties. So, right, in the Cartesian coordinate plane, if there's two lines, if the product of the two lines' slope is -1, then the two are perpendicular. But how do we derive a similar theorem for the complex plane? So let's define two lines, A, B, and C, D. So we have let's call the A is at complex number A, B is at complex number B, C is at complex number C, and D is at complex number D. So because AB is rotated 90 degrees to get to CD, so let's take the complex number B minus A. So this corresponds to shifting the entire coordinate plane such that A is now at the origin. So we shift these axes. When we subtract A, we essentially shift these axes so that A is now the origin. So we consider this complex number B minus A. It has some argument theta, right? So this has argument theta. And so now if we take D minus C, this has some argument. So now we're shifting the coordinate plane so that the origin is on C. This has the argument 90 plus theta. So that means B minus A and D minus C are rotated 90 degrees away from each other. So the condition to satisfy for perpendicular lines is simply B minus A times some r cis theta. So for some arbitrary r cis 90 equals D minus C. And so if we rewrite this, D minus C over B minus A must equal to r cis theta. But r is obviously some arbitrary real number. R says 90. But cis 90 is I. Right? So r times I is just an imaginary number. So this is the criteria for two lines to be perpendicular in the complex plane. D minus C over B minus A must equal a purely imaginary number. Alright? And then so a similar criteria applies for parallel lines, right? D minus C over B minus A must equal a real number, right? And we can derive that the similar way for parallel lines. The previous one was for perpendicular lines, right? Okay. So, any questions so far on these complex number properties? So these are just the basic properties of complex numbers. It's more important to see how to apply them. So now that we know how to convert from complex numbers, let's see how we apply this in geometry. So to do that, let's first go to the problems. And you guys all have the handout, right, that I sent in the classroom? Okay. So, alright, now let us go to the problems. Alright, okay. So, let's start at the top. Okay? So, a function f is defined in the complex numbers by f of z equals to a plus bi times z, where a and b are positive numbers. This function has the property that the image of each point in the complex plane is equidistant from that point and the origin. So given that a plus bi equals 8, and that b squared equals m over n, find m plus n. So you guys can obviously tell, right, this is an AIME problem. It's a past year's AIME problem. Okay, so let's break this down. So the function has a property that the image of each point on the complex plane is equidistant from that point and the origin. So let's just start a new line. Okay, so for the problem 1, okay, so the image of each point in the complex plane is obviously f of z, right? So the function has a property that image of each point is equidistant from that point and the origin. Okay, I'm going to go back to the Jamboard now. Alright, okay. So f of z is the image, right? And so the distance from the image to z, which must obviously be, so if we have, quick side note, if we have f of z is right here, and z is right here, how might we find the distance between these two? Well, the quickest way would be if we shift the entire complex plane such that z is now at the origin. So subtract z from everything. And so we move the complex plane such that z is now at the origin. So then what is the coordinates of this point? It's f of z minus z. And what is the distance from this point to the origin? It's just the magnitude of f of z minus z. So we have magnitude of f of z minus z. And this equals, and so this is the distance from the image to the original point. And so we're told that it's equal to the distance from the image to the origin. So we have this equals this equals f of z. Alright? So the distance from f of z to the origin is just the magnitude of f of z. So now let's apply let's break this down even further. So a common technique, right, the most important technique is always going to be just to write z as either r cis theta or a plus bi theta, or a plus bi. So let's use either of the two. So we're already given something that has to do with a plus bi. So let's break it down. And let's substitute for f of z. So a plus bi times z minus z equals a plus bi times z. So we can use the distributive property, right? This comes down to a minus 1 plus bi times z equals magnitude of a plus bi times z. Oops. A plus bi times z. And so we can split the two magnitudes again using the property of the magnitude. A plus bi times z magnitude equals magnitude of a plus bi times magnitude of z. And so neatly, magnitude of z cancels. And so we're left with magnitude of a minus 1 plus bi must equal to the magnitude of a plus bi. Alright, so now the magnitude of this side is obviously just, well, so to make this easier, we can square both sides, right? And so we have a minus 1 squared plus b squared must equal to a squared plus b squared. So b squared cancels, and then we have 2a plus 1 equals 0. So a equals 2, or 2a minus 1 equals 0. And so a equals half. Alright, so now that we have a equals half, so one more thing that we're told is that the magnitude of a plus bi is equal to 8. So this equals 8 squared. This is obviously 64. And so if a equals half, then a squared is 1/4 plus b squared equals 64. And so b squared equals to 255 over 4. Alright, any questions? Alright, okay. So another way we could have done this is by simple substitution. So this function has a property that for any choice of z, this is true. So if we can choose z to be an easy number, or easy complex number, then that might make our job a lot easier, or our computation a lot easier. So let's pick z equals to a super simple complex number, which is just 1 plus I. Right? Then f of z equals a plus bi times 1 plus I equals to a minus b plus a plus b times I. Right? And then so we have the magnitude of f of z minus z must equal to the magnitude of f of z. And so we can solve this too. And then it will give us the same answer. Right? Any question on that question? Okay. Alright, so let's move to problem 2. So this looks like a simple geometry problem to start. So the points 0, 0, A11, and B37 are the vertices of an equilateral triangle. So if we were to try using simple geometry, so we have 0, 0, A11, and say B37, and this we're told is an equilateral triangle. So if we were to try simple geometry, then one thing we might try is write all the sides are equal. So we have the distance from B, 11 to the origin, which is obviously square root of b squared plus 11 squared, equals the distance from A, this should be 37, and this should be 11. So b squared plus 37 squared equals square root of a squared plus 11 squared equals square root of Now a minus b squared plus 26 squared. Right? So this is a bunch of complicated equations. Right? So we could potentially solve these, but these are it seems like a lot of work, right? So this makes this problem a very good candidate for complex geometry. Mostly because this angle is 60 degrees. And so if we can see that a comma 11 rotated counterclockwise 60 degrees is simply b comma 37. So this rotation is also what makes it a good candidate for complex geometry. So let's try applying complex geometry here. So if we assume that a comma 11 is a complex number, a plus 11i, and so we take this and multiply it by, so now if we're rotating 60 degrees, that corresponds to multiplying by 660. And so this equals to, now b comma 37, which would be b plus 37i. Okay, so now if we multiply this out, right, cis 60 is, so cis 60 is cosine, so it's half plus root 3 over 2i. And this equals to b plus 37i. And so if we expand this, we get a over 2 minus 11 root 3 over 2. Plus 11 over 2 plus a root 3 over 2 I equals to b plus 37i. And so very simple now, just match the complex and the real parts. So 11 halves plus a root 3 over 2 equals to 37. And so we get, let's see, a root 3 equals to 63. And so a equals to 6 root, or 18, 7, 21 root 3. There we go. Okay. Okay. So this is some simple algebra now. So now we have a equals to 21 root 3. And then so if we plug this back in, we have b equals to a over 2 minus 11 root 3 over 2, which obviously equals 5 root 3. Right? And then so we're asked to find AB. And so AB in this case will be 315. Right? So notice how this problem was made drastically easier by using the complex geometry. So in the problem, there were no complex numbers hinted at, nor did they didn't mention anything about complex numbers. So it seems like a normal geometry problem. But in reality, it's a hidden complex number problem. And so let's see another example of this, which is number 3. So bug walks all day and sleeps all night. On the first day, it starts at point O, faces east, and walks a distance of 5 units due east. Each night, the bug rotates 60 degree counterclockwise. So that in itself just tells you, alright, we're looking at complex geometry here. 60 degrees counterclockwise. Okay. Each day, it walks in the new direction half as far as it walked the previous day. The bug gets arbitrarily close to point P. Okay. So basically, we're trying to find the location of the bug after infinite steps. Right? So obviously, there's going to be some sort of infinite geometric series involved. Okay, so let's call the coordinate of the bug as b. So first it starts at 0, right? So this starts at, okay. So let's let's do it without coordinates first. So just a normal geometry problem. So we start here, O, then we go 5 units east, and so we'll call this point O1. Then we rotate 60 degrees counterclockwise and move 5 halves units. So this is 5. This is 5 halves. So this is O2. Rotate 60 degrees again. So we go this way now. This is O3. This length is 5/4. Rotate 60 degrees again. We go this way. To where it's 5/8. This is O4. Alright, so this looks like a potentially doable geometry problem. So let's do it first using just geometry. So one thing we might do is let's try imposing it in normal coordinates. Alright, so we start with the normal coordinates. So let's look at the x value of the coordinate. Right, so the x value, first you add, so it starts at O, then you add 5, right? Then you add 5 halves times cosine 60. Then you add 5 halves times cosine 120, or 5/4. Then you add, let's see, 5/8 times cosine 180. Then we add 5/16 times cosine of 240. Then we add 5/32 cosine of 300. And then we add 5/64 cosine of 360. Alright, so finally the pattern has arrived because cosine 360 is now 1. And then if we keep going like this, you can see it's a geometric series where the first term is 5 plus 5 halves cosine 60 plus 5/4 cosine 120 plus 5/8 cosine 180 plus 5/16 cosine 240 all the way to 5/32 cosine 300. And then the start of the next term is 5/64 and so on. So you can see that this first part, so if we try computing this, so this is 5 plus now 5/4. This cosine 120, so this gives us minus 5/8, minus 5/8. So this actually cancels out nicely. And then plus 5/632 plus 5/64. And so we can compute this, right? And the common ratio is 1/64. Right, so we can compute the y value or the x value as you go to infinite steps. And then if you keep going, the y value, you can compute that too. So it's a very complicated process, right? But it's still doable. So now let's see how we do this using complex geometry. So we start with, obviously, complex plane, start at 0, as usual. So the first number we add is 5. So b equals to 5. Now the second number we add is 5 halves, but it's rotated 60 degrees clockwise. So we're going to add 5 halves times cis 60. Okay. And then the next number we add is 5/4 times cis 120. However, cis 120 is just cis 60 squared. Right, it corresponds to 2 rotations of 60 degrees squared. The next one is going to be 5/8 times cis 60 cubed. And you can see this is a very simple geometric series. And so this equals 5/1 minus. Now the common ratio is half cis 60. So this is super easy to compute. This is 5/1 1 minus 1/4 plus root 3 over 4, which equals to 5 over 3/4 plus root 3 over 4, or I. And then we get, let's see, 20 over 3 plus root 3I. And we get multiplying by, so we have 20 over 3 plus root 3I, and we multiply by 3 minus root 3I. This gives us 60 minus 20 root 3I over 12. And so this gives us 5 minus 5/3 root 3. And so we're asked for, so this is the limiting coordinate, 5 minus 5 root 3I. And we're asked for the distance from the origin to this point, so OB squared. So OB squared is just going to be the magnitude of B squared, because the magnitude of B is the distance from O to B. And so the magnitude of B squared is obviously just 25 plus 25 over 3. And so this equals to 100 over 3. So we're left with 103. That's our answer. Alright? So a lot of the times complex geometry problems are hidden in normal geometry problems, and any problem that's doable with complex geometry is also doable with normal geometry, obviously, but it's much easier to do it with complex geometry, as you saw. Our solution was much shorter than it was for the previous one, because the previous one, right, we had a bunch of infinite geometric series for x, and then one for the y coordinate, and so on, whereas for the complex geometry, we had a singular infinite series, very easy to compute, right? So the main thing to take away is, right, these complex geometry problems are hidden, and the kind of clues that clue you towards these kind of problems are the rotations, especially if it's counterclockwise, rotations, maybe reflections, and things like that, right? So let's look at number 4. So consider the region A in the complex plane that consists of all points Z, such that both Z over 40 have real and imaginary parts between 0 and 1, 0, 40, and 40 over C. Okay. What is the integer that is nearest the area of A? Okay. So if we look on the complex plane, right, to have a real and imaginary parts between 0 and 1, that corresponds to this square right here. So, hold on. Okay, so let's try a little bigger. So that corresponds to a square right here, where this is 1 and this is 1, right? So if Z over 40 lies in this square somewhere, that means that Z lies somewhere in this big square of side 40 and 40, correct? Okay, now let's see what we can do with the condition that 40 over Z also lies in this square. Okay, so let's take Z equals to A plus BI. That's always a good first step. So then 40 over Z equals to 40 over A plus BI. And so this equals to, so if we rationalize we uncomplexate the denominator, we get 40 times A minus BI over A squared plus B squared. And so the new number, 40 over Z, equals 40A over A squared plus B squared and minus 40B over A squared plus B squared I. Okay, so we have that both of these parts are between 0 and 1. So we have 40 over A squared plus, or 40A over A squared plus B squared is greater than 0, greater than less than 1. So this gives us 40A is greater than or equal to 0 is less than or equal to A squared plus B squared, or so the first one just gives us A is greater than or equal to 0. The second one gives us A squared minus 40A plus b squared is at least 0. And so this looks like the equation of a circle, right? So if we add a 400 to both sides, then we have a squared minus, or we have a minus 20 squared plus b squared is at least 20 squared, correct? So this is the area outside the circle, centered at 20, 0, and of radius 20. So if we go back to this drawing right here, so it's centered at 20, 0, so right here, and it has radius 20, so it's the area outside the circle. So what we're looking for is this area. Okay, now let's deal with the second condition. So we have 40b over a squared plus b squared, in fact, negative 40b over a squared plus b squared is greater than or equal to so we have negative b over 40, or negative 40b over a squared plus b squared is less than or equal to 0 and greater than or equal to 1. So greater than or equal to 1. So if we multiply by negative a squared plus b squared, we have 40b is at least a squared plus b squared is less than 0. And so the first part gives us b is at most 0, which, hold on. And then the second one gives us, so we have, let's see, a squared minus, okay, hold on. There is a typo, okay. Whoops, so this was in the, I kind of misread the question. This was 40 over z conjugate. That's what it was. And so this is a minus bi on the denominator. So in the numerator, it's a plus bi. So this is plus. And so if we go here, this should be plus. Okay, that makes a lot more sense. Okay, so we have, this is the exact same conditions as b as for a. So this gives b at least 0. And then we have b minus 20 squared plus a squared is at least 20 squared. So this is the area outside the circle, centered at 0, 20, and of radius 20. So if we draw this circle, it's centered right there. And we're looking for everything outside the circle. So we're looking for this area. Alright, so basically we just need to find the area outside of both circles, but inside the square. Alright, so this is just a well-known geometry problem, right? So we can do this. So this reduces down to the problem. Find the area inside a 40 by 40 squared outside of these semicircles. So this is 40 and this is 40. Alright, so let's do this by dividing this into a bunch of regions. So this part is just a quarter circle, and so is this part. And this part right here is a square, right? So the area inside both of these circles is equal to, so this is 20, so we have 20 squared pi over 2 plus 20 times 20. There inside the whole square is 40 times 40. And so if we subtract 40 times 40 minus that, we have 1600 minus 400 minus 200 pi. We end up with 1200 minus 200 pi. And so it's asking us for the integer nearest the area of A. So if we compute that, that comes out to be like 572. Right? So about that. Alright? So pretty easy. That's not a tough problem. So let's take a look at the next problem. So this problem is significantly harder. Alright. So a regular hexagon with a center at the origin in the complex plane has opposite pairs of sides 1 unit apart. One pair of sides is parallel to the imaginary axis, and let R be the region outside the hexagon, and let S be the region that consists of the points 1 over Z, where Z is in R, and then we want to find the area of S. Alright, so let's draw a good diagram. Even though this is complex geometry, like with all geometry, you should always start with drawing a good diagram. Alright, so we have a hexagon. This length is half. So this length is 1 over root 3, right? And this length is 1 over 2 root 3. Alright, so we have a couple lengths. So let's see what we can do. So basically, we want to find the area of the region outside this hexagon when you take the reciprocal of that of each complex number of that region. So let's consider the symmetry here. So we can divide this hexagon into 6 triangles, right? It's obviously equal. All the regions are equal. So if we extend these lines, we can divide the entire coordinate plane into 6 regions. And so all we need to do now is we want to find the area of S corresponding to each region. And if we multiply by 6, then we should get the total area, right? By symmetry. So let's do this. So let's consider just one region, and the easiest region obviously looks to me like this region, unless you see an easier region. So let's redraw this and get rid of all the clutter. Okay. So let's look at one of these 6 regions. And let's try to figure out what shape S is going to be. So we have an equilateral triangle, like this, right? Same dimensions. And so if we extend these lines, what are we going to get? Okay. So if I draw this circle, if I draw the circumcircle of the hexagon, right? This circle is it's basically defined in polar coordinates by the function r equals 1 over root 3, correct? So every point outside of the circle, this consists of the points in this 1/6 sector that have r greater than or equal to 1/3, 1 over root 3, right? So for all points that r is greater than or equal to 1 over root 3, then this is going to, when we consider all points that satisfy this, then 1 over z obviously satisfies r is at least root 3, or r is at most root 3, correct? So here, let me make this easier. So if we let w equal to 1 over z, so for z, so r of z is at least 1 over root 3, correct? So then r of w is going to be at most root 3, right? So that corresponds to a circle somewhere in the sector like this, correct? So now one more thing to consider. So what exactly is w? Well, w equals to 1 over z, right? And we know that z equals to r times cis theta. So it's equal to 1 over r cis theta. And the conjugate of cis theta is clearly just cis of negative theta, right? And you can check that if you want. It's just cis of negative theta. So if we multiply the numerator and denominator by cis of negative theta, this gives us 1 over, or this gives us cis of negative theta over r. Okay, so the point w really corresponds to taking z, dividing by r squared, and r squared obviously equals the magnitude of z squared, and then reflecting it about the y-axis, or x-axis, correct? We have cis negative theta on the top, and so this is the same as z conjugate over z squared. So basically we're taking z conjugate, and then we scale it down by a factor of magnitude of z whole squared, correct? Okay, so now let's see where that takes us. Okay, so first thing to note is that in our sector, in our little 1/6 sector, right? Any point on this line is just going to be reflected and scaled, so it's somewhere around there. And every point over here is somewhere going to be around there, or is going to be reflected, so it's like this. So any point in this sector will stay in this sector, correct? Because all that we're doing is we're flipping it across the y-axis, and then we're scaling it towards the origin. So we're only negating its argument and then scaling its radius. So every point in the sector will stay in the sector, and then we already established that every point outside here will map to a circular sector of radius root 3. Okay? So now we still haven't considered what about these points in this little sector right here. Okay. So let's see what we can do about that. So let's first consider this line of the hexagon. So what exactly happens to these points that lie on this line? Well, the line is defined by z, or the real part of z, equals half, correct? So we have the real part of z equals half. So the real part of z equals to z plus conjugate of z times half, right? Equals half. So the real part of z plus conjugate of z over 2 equals half, right? And so we have the real part of z plus z conjugate equals to 4, or 1, right? And so what does this tell us about w? Well, if we plug in, okay, hold on. I gotta create another jam slide. Or Jamboard. Oops. No, did not want that. Alright, okay. So anyways, back to what we're doing. So we have the real part of z plus z conjugate equals 1. So what does this tell us about w? Well, if we plug in w here, it was, okay, hold on. So we had the real part of z is half, and the real part of z is equal to z plus z conjugate over 2 equals half. So we have z plus z conjugate equals 1/4, or 1. Okay, so what does this tell us about w? Well, w equals 1 over z, right? So z equals to 1 over w. So if I plug this in here, then we have 1 over w plus 1 over w conjugate equals 1. Okay. So this gives us w plus w conjugate equals w times w conjugate. Interesting. So what can we say about w? Well, this this equation right here doesn't really stand out as some sort of interesting. Oh, what the? Okay, hold on. Okay, alright. Good thing I checked the chat. Alright, you guys can see it now? Is it good? Okay. So anyways, so what I was saying is, right, we started off with this. Real part of z is equal to half. And the real part of z is just equal to z plus z conjugate over 2. So I mean z plus z conjugate equals 1. And so we have 1 over w plus 1 over w conjugate equals 1. And so this gives us the equation for w, which is w plus w conjugate equals to w times w conjugate. Okay, so where do we go from here? Well, this equation doesn't really stand out as some sort of like circle or line or geometric figure. So when in doubt, substitute w equals to a plus bi. So let's plug that in here. So we have a plus bi plus a minus bi, or which is 2a, equals Okay, let me do this on the next slide. So if we plug that in, we get A plus BI plus A minus BI equals to A plus BI times A minus BI, which gives us 2A equals to A squared plus B squared, and this gives us, obviously, this looks like an equation of a circle, right? And we can convert this to A minus 1 squared plus B squared equals 1. Nice. Okay. So for W, if Z lies on this line represented by the hexagon, so if we're looking better at our sector, this line right here corresponding to the real part of Z is half. That line maps onto this circle, which is a circle of radius 1 centered at 1, 0. So it's something like this. And so it's centered, it looks basically like that, right? And so, interestingly, so I'll save you from the algebra and geometry, but if we, when we look at this, so we already established that, so there's a circle here, right? Every point outside this circle lies inside, after it's mapped, it lies inside this point right here, correct? And so this line, we established, maps onto this circle, correct? And so this circle, it turns out, if you draw it, it looks like this. And since we're only considering a portion of the line, we only consider a portion of the circle. So it maps exactly like this. And so it's not that far to then assume that everything in between just maps in between. And so what we're looking at is this sort of ice cream cone type of thing. So this basically, we need to find the area of this figure, right? So this is root 3. This outside circular arc is a radius of circle 1, like this. So it's an arc of a radius of circle 1. So this is 1, this is 1, this is root 3, right? So this is a 120-degree arc. And so from there, it's pretty simple to find the area of the entire figure and then multiply by 6. Alright, so any questions on that? That was a relatively complex problem. No pun intended. Yeah, it was quite a bit harder. Alright, so let's go on to the 6th problem. Okay. Circle C0 has radius 1, and the point A0 is a point on the circle. Circle C1 has radius R, less than 1. Circle and is internally tangent to C0 at point A0. Point A1 lies on circle C1, so that A1 is located 90 degrees counterclockwise from A0 on C1. Circle C2 has radius R squared, and internally tangent to C1 at point A1. And then, so like you keep constructing, circle CN has a radius. Okay, so this problem looks a lot like problem number 3, where we were adding and rotating and a bunch of circles, and we're eventually finding the limiting point after we go n to infinity, right? So this looks a lot, this heavily, the problem is telling you to use complex geometry. It doesn't have complex numbers in it, but it's telling you. It wants you to use complex geometry. So let's see what we can do with this. Okay. So we start with setting the origin. So the most obvious choice of origin would just be C0 at the center of the first circle. So we set this as the origin, and nicely enough, this point is defined to be, or this circle is defined to be a circle of radius 1, which makes everything simple. So circle C0 is defined, or C1 is defined like this, with the radius R. So the coordinates of C1 are, no pun intended again, are 1 minus R, correct? Because it's 1 to A0 and then minus R. Okay. So now, to get from C1 to C2, we're going up this time, right? We're going up. So this is equal to C1 plus, now this length length from C1 to C2 is, length from C1 to C2 is R minus R squared, correct? And then we multiply by I, because we are moving upwards rather than to the right. So then we're moving directly vertical upwards. We multiply by I. Okay. So now what about C3? Well, C3 is equal to C2 plus, now this time we're moving to the left, and we have R squared minus R cubed, because the radius of C2 is R squared, radius of C3 is R cubed. Okay. So, and then this time we're multiplying by -1, because we're moving to the left, rather than up, down, or to the right. Okay, so now C4 equals to C3 plus, now C4, the radius of C4 is R to the 4th, the radius of C3 is R cubed, right? So we have R cubed minus R to the 4th times, now we're moving down, which is multiplying by -I, correct? So if you can see this, if we expand this, so this looks like we start with 1 minus R, and then we add R minus R squared I, and then we add R squared minus R cubed times -1, and then keep going. So we really want this to be a geometric series. So one thing to note is that the 1 minus R factor is in all of these terms. So if we take out 1 minus R, this gives us 1 plus Ri plus R squared times -1 plus R cubed times -I, and so on. Now this equals Ri plus R squared I squared plus R cubed I cubed, and so on. And this is obviously just a simple geometric sequence. So this is 1 over 1 minus Ri. Sorry, I don't know why I did that. Should be times times. Alright, there we go. So our final answer is 1 minus R over 1 minus Ri. So that's the location of the center of the circle when we go all the way to infinity. Okay. So now if we just compute that, so we'll just compute this in terms of I. So 1 minus R over 1 minus R times I. And if we rationalize, or we uncomplexate the denominator, this equals to 1 minus R times 1 plus Ri over 1 squared plus R squared. And so this equals 1 minus R over 1 squared plus R squared times the complex number 1 plus Ri. And so the distance from this point, this complex number, to the origin, which is what we're looking for, it's just going to be the magnitude of this, which equals to 1 minus R over 1 squared plus R squared times the magnitude of this inside term, which is square root of 1 squared plus R squared. And so this cancels out nicely, and we end up with 1 minus R over square root of 1 squared plus R squared. And if we plug in R equals 11 over 60, we end up with 49 over 61. And so that is what we're looking for. Alright, any question? Any questions? Okay. Some of you are confused. Should I explain? Do you want me to explain it again? Okay. Alright. So let's move on to the last two questions. Alright. So we have our last three. So let V and W be distinct randomly chosen roots of the equation z to the power of 1997 minus 1 equals 0. Let m over n be the probability that the magnitude of v plus w is greater than that number, where m and n are relatively prime positive integers. Alright, so before we tackle this problem, let me introduce the roots of unity. So basically, right, we're considering the roots of the equation z to the power of n minus 1 equals 0. Right, when n equals 1, there's only one root, z equals 1. N equals to 2, there's 2 roots, z equals to 1 and negative 1. When n equals to 3, however, you have z cubed minus 1. We factorize this, we get z minus 1 times z squared plus z plus 1 equals 0. The first one gives z equals to 1. Now the second one is a quadratic. This has complex roots. Right, so we get z equals to negative 1 plus or minus square root of 1 minus 4 all over 2, which equals to negative 1 plus or minus root 3i over 2. So these are the three solutions for n equals to 3. Z equals to 1, and z equals to negative 1 plus or minus root 3i over 2. And then n equals to 4. We can factorize, and we'll get z equals to plus or minus 1 and plus or minus I. Alright? So that's for low powers of n. But what happens when we get to large powers of n, for example, like 1997? Is there a general solution for this? So remember that any complex number, right, so now we're considering that all the roots are complex, so any complex number can be written as r cis theta, and this is the same as e to the power of I theta, correct? So now e to the power of I theta, if we plug this into the equation, we get e to the power of I n theta minus 1 equals 0. And so if e to the power of I times n theta minus 1 equals 0, that means that since e to the power of I n theta equals 1, and e to the power of I n theta also equals to cosine of n theta plus I sine of n theta, I sine n theta, and this equals to 1. And if we match up the real and the complex terms, we end up with sine of n theta equals 0, and cosine of n theta equals 1. So what is the solution to this equation? Sine of n theta equals 0 and cosine of n theta equals 1. Well, the solutions are n times theta equals to 0 degrees, right? And then, so actually 0 radians. And then we could have 2 pi radians. And then we could have 4 pi radians, right? So the solutions are, in general, k times pi radians, correct? Or 2k times pi radians. So in general, the solutions are theta equals to 2k pi over n, where k is an integer, correct? Okay, so now this equation, right, this is subject to, like, you can't go over 360, right? Otherwise, you're considering the same angle over and over again. So basically, the solutions are going to be 2 pi over n, 4 pi over n, 6 pi over n, all the way up to the largest value of k, which would be 2 times floor of n over 2 pi over n. So this is all the solutions to this equation, z to the power of n minus 1 equals 0. These are known as the roots of unity because, well, you're looking at the root of when z to the power of n equals the unit, I guess. Alright, so now if you graph this on the complex plane, so if we consider for n equals to 2, or n equals 1, right? That's just the 1 point right there. N equals to 2, we have 2 points, this one and that one. N equals to 3, we end up with 3 points. The 1 is still there, and then we have these two. N equals to 4, we end up with 4 points, like that. N equals to 5, we end up with 5 points, and you can see like it forms, the roots of unity form a n-gon on the complex plane, centered at the origin, and with one of the vertices equal to 1, right? So now, okay, let's go back to the problem. So let v, oh, actually, one more thing. So for any of the roots of unity, right, all the roots of unity are equal to e to the power of I times theta, where theta is one of the solutions. So this equals to cis theta. So what is the magnitude of z? The magnitude of z equals to the magnitude of cis theta, which obviously equals 1. So the magnitude of any of the roots of unity is equal to 1. So all the roots of unity lie on the unit circle, and they have their magnitude equal to 1. Alright. So now let's consider this problem. So v and w are distinct randomly chosen roots of the equation where n equals 1997. So we want to find the probability that 2 plus root 3 is at most v plus w. So, right, since we're dealing with probability, let's just, without loss of generality, let's choose v equals to 1. That'll make our job a whole lot easier. So v is right here, 1. And so w has a bunch of possible choices. It can be anything from anything all around the circle, satisfying one of the roots of unity, right? So let's look at how do we get the magnitude of v plus w. So if I have a general complex number v right here, and say w right here. So v plus w is going to equal, I don't know if you guys are familiar with vectors, but it essentially equals some point right here, such that this is w, right? Or if I subtract v from each point, then this, right? If I just translate w over, like that, so w corresponds to this vector. And so if I translate this vector so that its head, or the end of the vector lies on the arrow of v, this vector from the end of v to the arrow of w is going to correspond to v plus w. And so the lengths of vectors correspond to the magnitudes of the complex numbers. So this just corresponds to a triangle. And so this is obviously subject to cosine law. So we have the magnitude of v plus w, this is just a general formula, is equal to the magnitude of v plus the magnitude of w minus 2 times the magnitude of v times the magnitude of w cosine theta. Alright, so now let's use that. So, squared, right? I forgot the squareds. Okay, magnitude of v plus w squared equals magnitude of v squared plus magnitude of w squared, and so on. Okay, so now let's use this. So we have 2 plus root 3 is at least magnitude of v squared plus magnitude of w squared minus 2 times magnitude of v, magnitude of w, cosine theta, where theta is the angle between v and w, right? And so v squared is 1, w squared is 1, v is 1, and w is 1. Or the magnitudes are 1. So this gives us root 3 should be at most 2 cosine theta. And since we already chose v equals to e to the power of I times 0, or v equals to 1, and we have the choices for w are e to the power of I times 2k pi over n, where k can be any integer from, or 2k pi over 1997, where k can be any integer from 1 or 0 to 1996. So k equals 0. And so we can count relatively easily the number of solutions satisfying that. Alright, any questions so far? Okay, alright, let's quickly do the last two problems then. So given f of z equals to z squared minus 19z, there are complex numbers with the property that z, f of z, and f of z are the vertices of right triangle in the complex plane with a right angle at f of z. There are positive integers m and n such that one such value of z is m plus root n plus 11I. Find m plus n. Alright, so there's many ways we could do this. Right, one way we could do this is, so z, f of z, and f of z form some sort of right triangle like this. So we might think to apply Pythagorean theorem, but that's going to be relatively computation heavy, right? Because the main idea behind complex geometry is to make it easier for rotations and translations. And so dealing with length in complex geometry is not ideal because the distance formula is quite complicated, right? It's the magnitude of f of z minus z, which has there's no like general expansion for that. So rather than deal with that, let's deal with the angle part of this, which is that this angle is 90. So remember I said earlier that the criteria for two lines to be perpendicular is that so if we have two lines, AB is CD, A, B, C, D, the criteria is B minus A over C minus D must be a purely imaginary number, right? So it does not have any real part. So let's apply this to that. Alright, so we have f of z minus f of z over f of z minus z must equal an imaginary number, pure imaginary number. Okay, so let's see if we can simplify this. Let's plug in the definition for f of z. So f of z, well first, f of z equals to z times z minus 19, right? So f of z, so f of z equals to z times z minus 19 times z times z minus 19 minus 19, right? Okay, so let's see what we can do with this. So f of z minus f of z equals to z times z minus 19. To make this easier to see, I'll just write this f of z, and this is f of z. And so we can obviously plug in the definition of f of z, but this is true. All right, so we have f of z times f of z minus 19 minus f of z. And so rather than expand it, I want to factorize it because we shouldn't expand until it's necessary. Otherwise it gets kind of messy. So if we distribute, we get f of z times f of z minus 20. Alright, and then we have f of z minus z. This equals to z times z minus 19 minus z, which equals to z times z minus 20. Alright, so now on the top we have f of z times f of z minus 20 over z times z minus 20. And so if we plug in the definition for f of z, this gives us z times z minus 19 times z squared minus 19z minus 20 over z times z minus 20. And obviously this factorizes. So we end up with z plus 1 times z minus 20. And so this cancels, and this cancels. So this nicely cancels. And so we're left with z minus 19 times z plus 1 must be a purely imaginary number. Alright. Now let's use some more information. So to proceed from here, is going to be very hard, right? So let's use the definition z equals to a plus bi. That's always useful. So let's plug this in. Well, one more thing. We know that b is equal to 11, right? So z equals to a plus 11i. So let's plug this in, and let's expand. So z minus 19 equals to a minus 19 plus bi, and z plus 1 equals to a plus 1 plus bi. And so if we expand this, we get a plus 1 times a minus 19 minus b squared. Should be 11i, right? 11 squared. That's the real part. And since we want this number to be imaginary, we want the real part to be 0. So we set this equal to 0. And so we get, right, a squared minus 18a plus 19 minus 120, or minus 19 minus 121 equals 0. And so we have a squared minus 18a minus 140 equals 0. And this is a simple quadratic that we can solve for and get the answer that we need. Alright, so any questions? Okay, alright, so the last problem is actually a proof problem. Quadrilateral, oh yeah, sorry, you had a question? Gumball Dumbball? Okay, never mind. Okay, no one has questions, right? Okay. Alright, so the last problem is interestingly a proof problem. Quadrilateral APBQ is inscribed in circle omega with angle P equals to angle Q equals 90. As always, draw a good diagram. And we have AP equals AQ is less than BQ. So this is B, A, and then P and Q. Something like this. And then we have X is a variable point on segment PQ. So it could be something like this. Line AX meets omega again at S. So draw this, meets at S. T lies on AQB such that XT is perpendicular. So this is T. This is perpendicular. And then M is the midpoint of chord ST. This is M. And we wanted to show that as X varies across all of segment PQ, M moves along a circle. Alright, so this is not an AIME problem, as you might be able to tell. This is actually a US AMO problem. And the reason I included this on here is it looks like a pure geometry problem, right? But there's actually an interesting way you can do this with complex geometry. And so, just as a quick example of how we might be able to apply complex geometry in proof problems like complex bashing. So, if you have heard of that, I've included this problem. Alright. So, this is a very, it's a very involved problem. So let's first try and develop a hypothesis of what we think, or what the circle we think is, right? M varies along a circle. So what could that circle be? Well, if X is equal to this point right here, then the circle is, right, if X is equal to the point where AB and PQ intersect, then M is simply the midpoint of QB, right? Because T is Q and S is B. So M is the midpoint right here. And then let's see, we have, if we go on the other side, so clearly this is reflective, right? So that means the circle is centered along AB, correct? M, we can simply reflect X across AB, and we get an equivalent point of M. So that means the circle is centered somewhere along AB. Okay, So let's see what else we can do. So M could also be above PQ. It could be below. It could be on AB, right? Okay. So the central claim that I claim that M varies along this circle, where the center is this point right here, which is the midpoint of, or it's the quarter point of AB. So we'll call the center of the circle O, and so we claim that the circle that M varies upon is AO. Alright? So let's see how we can prove this using complex numbers. So the way we're going to do this is first, let's put the circle on the complex plane, and let's make it the unit circle. Right, so it's the circle of radius 1 on the complex plane. So to make things easy, we put A at -1, B at 1, and P and Q are something like this. And then we put S at, so we draw X. So S is something like that. Right, T is something like that. X, and M is something like this point. B. Okay. So now in terms of, so each of the complex points we'll just call the lowercase letter of the point that it's referring to. So we have M is equal to half S plus T. So what we're trying to prove is that the distance from M to this point right here, which is -half, is constant. So we're trying to prove that M plus half squared is constant. And so what we're really trying to prove is that S plus T, so magnitude of S plus T plus 1 over 2 is constant. That's what we're really trying to prove. Alright, so that's squared, and so if we square that, we get, let's see, 1/4 times, so we have 1 plus S squared plus T squared plus 2S plus 2T plus ST, right? And so, very involved problem, right? And so, basically, actually, rather than doing that, let's do it, let's take the conjugate, so this should be S plus T plus 1 over 2 times the conjugate of S plus T plus 1 over 2, right? And so this equals to 1/4, there's extra 1/4. No 1/4. Alright. And so this equals to S plus T plus 1 over 2 times S conjugate plus T conjugate plus 1 over 2. And so this equals to 1/4 of, now we have 1 plus S times S conjugate plus T times T conjugate plus S times T conjugate plus T times S conjugate plus S plus T plus S conjugate plus T conjugate, right? So we have 9 terms, as there should be, correct? And so S times S conjugate, this is equal to the magnitude of S squared, which is just 1. Same with T times T conjugate, this is 1. S times T conjugate is equal to S over T. Right, so let's replace this with 1, 1, 1, plus 1, plus, now this is S over T. T times S conjugate is T over S. S conjugate is 1 over S, and T conjugate is 1 over T. Alright, so we're good so far? Okay. So basically, we want to prove that this value is constant. And the only thing we have to go off of is that the real value, or the real part of x, is constant. Right? PQ is parallel to the x-axis. And since x lies on PQ, we have the real value of x is, or the real part of x is constant. So somehow we have to take this and convert it into this being constant. Okay, so let's see how we can do that. Well, so first let's derive a formula. So first we have that, let's derive a formula for the reflection of a point Z across a line AB. So in general, so this is a divergence. If we have a line AB and we have a point Z, what is the reflection of this point Z across the line AB? So we'll call that W. So this is Z, this is W. So to do this, let's first shift everything to the origin. So this is now B minus A, Z minus A, W minus A, right? So we have 2 points. And then let's scale everything so that now we're talking about, let's divide everything by B minus A so that we look at, so we convert it to, this is 0, this is 1, and then so on the top, this point refers to Z minus A over W minus A. And at the bottom, the reflection of this point across the line is this is B minus A. So this is W minus A over B minus A. And so we know that now these 2 points are conjugates of each other. So we have W minus A over B minus A equals the conjugate of Z minus A over B minus A. Right? Okay. And so we can rearrange this to get W in terms of Z. And then to find this point right here. This point is the foot of the perpendicular from Z to the line AB, right? And this point is simply going to be half of W plus Z, correct? And so if we find W in terms of Z, then we can plug in that formula to get the foot of the point Z onto the line AB in terms of Z, alright? And so I won't state that formula exactly, but basically what we'll end up with is we can find the foot of the perpendicular from a point to a line given the 3 points, right? So going back to our problem, we have A, we have PQ, we have X, S, X, and T. And so, like I just said, X is the foot of the perpendicular from T onto line AS. So applying the formula that we derived, or that we would have derived if there was more time, we end up with X equals half times A plus S plus T minus A T times S conjugate. So this is what we would end up with. And so if we simplify this, we get X equals to half times A, or A is just -1, right? So this is -1 plus S plus T over S, right? And so we know that the real part of X is constant. So real X is constant. And so the real part of X is equal to half times X plus X conjugate. So if we plug in the formula we found for X, we get half times, the formula was, let's see, -1 plus S plus T over S plus the conjugate of this, which is equal to, right, the conjugate of -1 is just -1. Conjugate of S is equal to 1 over S. Conjugate of T is equal to 1 over T. Conjugate of T over S is S over T. So we find that this is equal to, this is constant, right? Alright, and so basically the idea is if we then plug this back into, so this quantity that we're trying to prove constant looks very similar to the quantity that we know is constant, which is this. And so eventually we'll end up with that the distance from M to the point -½ is equal to 5/4 plus RE of X. And that is constant, so M lies always on that circle. Alright, so a quick application of complex geometry to now proof problems, so not just AIME problems. All right. Okay, so I think that's all for today. Pretty dense topic. I would encourage you to go back and work through the problems yourself. That's your homework, especially that last problem. If you can work through that, you've understood complex geometry completely. So I'd encourage you to go back and work through them. I will upload the recording and these solutions soon. All right. So I'll see you next week. Bye. If you have any questions, you can ask.